this is what we have. The first thing that we have is called an upper and lower bound test. Upper and lower bound test. So you're gonna want to write that down. And this right here, all right. You don't necessarily need to write all this down because this right here is gonna explain what this says up here. All right. So again, upper and lower bound tests. So what this is going to do is, I'm going to draw a picture real quick. Is if we are, let's say we have a polynomial, right? So I'm going to come back up to this real quick, just a second. Let's say we have a polynomial and this graph looks like this. All right? 1, 2, 3, 4. 1, 2, 3, 4. All right. Now, this polynomial, you never know, might have a whole bunch of possible zeros. There might be a list that has like 40 possible choices. All right. And some of them might be really high, like higher than 4. So like 1, 2, 3, 4. But maybe you have a choice that's a positive 50. All right. Who knows? Now, what the upper and lower bound test allows us to do is, for instance, let's say the number 4 was a possible choice. All right. So let's say 4 was a possible rational zero. What the upper bound and lower bound test allows us to do is, when you do synthetic division, you get those numbers at the bottom. And based on what those numbers are, it will tell you whether or not that number is an upper bound or a lower bound. All right? If a number is an upper bound, that means that, right here, let's say x equals 4, turned out to be an upper bound. That would mean that any number that's higher than 4, there's no way it's a 0. A rational 0. So let's say you have like 1, 2, 3, 4, and then you still have like 12, 15, 19, 20, 50, I don't know, just random numbers, just throw numbers out there. If I found out that 4 is an upper bound, I know that none of those could possibly be 0. I just crossed them. They're not possible choices anymore. So I don't need to worry about testing them. All right? The same thing works with the lower bound. Just to say these are negative. Let's say let's just pretend all these are negative 2. If I found out that negative 3 was a lower bound, that tells me that negative 4, and oh no, none of those numbers would be. Anything lower than negative 4 is also not a 0. Alright? So it can allow you to cancel out a large chunk. And it also allows you to do, like, let's say we found out that let's say negative 3 wasn't a 0. Well, do I need to keep testing all these other negative ones? No, because it's the lower bound. So I know that all the zeros, all the rational zeros at that point are less than negative 3. All right. So how do you figure that out? Well, so what we have is C is that number. All right. So C, in this case, that is our possible 0. All right. So possible 0. So same thing down here. This C is our possible 0. So what this says is, if you do synthetic division, all right, and you come down here and it goes positive, 0, or if it goes positive, not positive, positive, not positive, positive, not positive, so if it alternates that way, all right, then that means that it is a lower bound. Yeah, the reason I have 0 here is because it is 0 is not positive. All right. So what it's saying is, if the numbers in the synthetic division, if they alternate positive and not positive, okay, they alternate between non-negative and non-positive, then it's a lower bound. All right. Now, if, all right, every number that you get is non-positive, or non-negative, is a upper bound. So if everything is positive or 0, that means that number you have found is a upper bound. Alright, so everything is non-negative, that means it is a upper bound.
So, does the 0 have to be right here?
No, it could be anywhere. I'm just showing that, okay, 0 is non-negative. It's also up here is non-positive. So let's say you're testing your positive, you find all your positive zeros, right? And you test, let's say, 5. And you use synthetic division, you get, it goes non-negative, non-positive, non-negative, so it alternates between being non-positive and non-negative, that means it's a lower bound. If it alternates between being, or not alternates, if they're all non-negative, that means it's a upper bound. So again, in this case, there's not going to be anything that we're doing new. All right. The next couple, everything you do the same thing, and then you just use this to cancel out some things. We're still going to use the rational zero theorem to find the possible zeros. We're still going to use synthetic division to actually determine if any of them are zeros. This is going to allow us to cancel out. Yes. Yeah.
Okay, so after the possible and the
Yeah.
lower bound, say the 0 is positive place, so let's say for the lower bound.
Here?
Yeah.
Right here. Yeah.
No, or the second.
Yeah, first of all, this will never be zero.
Yeah, I know that.
Because the leading coefficient always goes there, and the leading coefficient can't be 0. So if it was here,
Yeah.
so if this went positive, negative, 0, negative, yes.
Okay, so 0 is really not doing that.
0 is considered non-positive and non-negative, so as long as it alternates there, as long as you don't have 2 positives next to each other or 2 negatives next to each other.
So if I do
Well, let's say this said negative. Okay, first, if we had one that said this, so we got positive, positive, negative, positive. Okay, first of all, this is not an upper bound because they're not all positive. Or there's a negative. If there's a negative, there's no way it's going to be an upper bound. Alright? And it's not a lower bound because they don't alternate. Makes sense? So this right here, if this happens, that means, well, I can't rule anything out yet. I better keep going.
so it's possible. What if there was 2 zeros next to each other, like one is a negative and one is a positive? So that's still your one back.
So do it.
Positive 0, 0.
This ain't good, that's even possible. Oh no, that's the exact one. Let me think about that. I'll let you know about that on Friday. Alright. Comment on the Google Classroom, make sure I remember. Alright, question about that. Let's look at an example. Alright, so, alright, well, first of all, what we're going to do here is, it says determine an interval in which all real zeros must lie. Alright, Explain your reasoning using the upper and lower bound test. Then find all of these zeros. Okay? So, alright, that's all right. Alright, so we're gonna look at this and we're going to do this a little bit of a longer way. We're going to first start by looking at the graph of this equation. Okay? So, let me see, I gotta do. You guys should have your calculators out. I want you guys to go ahead and grab that graph. Alright, that function. So, it is y equals 2x to the fourth minus 11x cubed plus 2x squared minus 44x minus 24. And I'm going to do, I'm going to regraph this. You guys all have your graph? What's it look like? Alright. Like that? Let's do zoom. Let's see if we get zoom 0. See if zoom 0 helps. Yes, no. Let's do this. Let's go here. Let's do 100. Okay. Oh no. Whatever. We'll use my graph. Okay, it goes down further. That's cool, whatever. We know it goes down there. So you graph the function. So first of all, let's look at this. First of all, how many zeros does this function have? How many zeros does this function have? It has 4 zeros. Why is that, Nicola? Because the highest degree is 4. It has 4 zeros, 2 of which are real. The other 2 are imaginary. They're non-real. Alright? Hopefully you've heard that before. So, right now we're only concerned about real zeros. So, in this case, we can see it has 2 real zeros. Now, my first question would be this. How do we know that it only has 2 real zeros? How do we know that it doesn't go up here and come back down and go up here? How do we know that that doesn't come back down here and cross the x-axis? No, it's not within this window. Yeah, I could zoom out, have something that looks similar to this, and then say, well, how do we know that over here it doesn't come back down? How do we know? Not going anywhere. All the information you need is on this board right now. And that's going to get you yellow. How do we know it doesn't do that? we know what the degree. Oh, it does involve the two and it involves the highest degree. So the degree is positive. So if that tells me, I'm not concerned. The degree, yes, it is positive. The degree is always positive at all. The degree is positive. It's also what? Huh? Even. There we go. It's even. Even polynomials. That tells me that the end behavior is either going to go up, or down, In this case, we can keep zooming out. See, we don't know what happens out here. But it is a positive 2. When the degree is positive, remember when the degree is even, and when the leading coefficient is positive, that tells us that the function, the graph is going to, as x approaches negative infinity, y goes up. Limit as x approaches positive infinity, y goes up. So I know it's not going to come back down. Alright? So, now by looking at this, I believe our x-axis is counting by ones. Alright? It says, looking at this graph, can you guys tell me, first of all, what number might possibly be a lower bound and what number might possibly be a upper bound? What do you say? 1, 2, 3, 4, 5, 6. Well, 6 is upper bound, or 6 might possibly be a 0. Let's try 7. So let's estimate upper bound 7. What would be a lower bound? -1. Okay. So let's test it. So first of all, let's look at 7. We're going to use syntax division 2, -11, 2, -44, -24. Yeah. So bring 2 down. 7 times 2 is 14. -11 times, or -11 plus 14 is going to be 3. 7 times 3 is 21. 2 times 21, or 2 plus 21 is 23. 7 times 23 is much bigger than 44. Quickly, someone do it. 7 times negative, or 7 times 23. 161. -44 plus 161, go. 117. Alright, what's 7 times 7? Can we all agree that 7 times 117 is going to be a really big positive number? Like much bigger than 24, right? So it's going to be really big. So if I have -20, really big positive. If I have -24 plus a really big positive, that's going to be a positive number, right? Positive, 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 positive. These are all non-negative. All of them are non-negative. Therefore, 7 is an upper bound. Alright? So there are going to be no zeros higher than 7. None. Alright? So we said -1 is our lower bound, right? Let's test that. Bring the 2 down. -1 times 2 is -2. That's going to be -13. -1 times -13, that is going to be positive 13. That's going to be 15 right here. -15. That's going to be -59. 59. That's going to be 35. Alright. Does this alternate between non-negative and non-positive? Yes. So non-negative, non-positive, non-negative, non-positive, non-negative. So therefore, this would be a lower bound. That means that there are going to be no zeros below that. Now, let's check that. Alright, so first off, we're going to use the rational zero theorem. We're going to find out which of these rational numbers are possible, like, which of these possible zeros are actually zeros. So we're going to factor negative 24. We're going to plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 8, and how to drop 4 and 6. We're going to factor 2 as well. Plus or minus 1, plus or minus 2. Alright? Now what do we do after we get these numbers? Not yet. We gotta divide 3 by 2. Alright? So we're gonna have 1 divided, so we're gonna have all those. Then we're going to have 1 divided by 2, which is plus or minus 1/2. We're going to have 2 divided by 2, 1. 3 divided by 2, plus or minus 3/2. 8 divided by 2 is going to be 4. 4 divided by 2 is going to be 2. 6 divided by 2 is 3. Yeah. Alright. Here we go. Those are our possible zeros. Now, we just said anything lower than negative 1 cannot be a zero. Alright, well, that's gone. That's gone. All of these are gone. Okay. And that's gone. Cool, so we just know we almost eliminated half the possible choices. And we know anything bigger than 7 is out of there. That's completely gone now. That's completely gone. That's completely gone. Alright? So instead of having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20 choices to look at, we now have 2, 3, 4, 5, 6, 7, 8, 9. Alright, now, let's look at it. So I like to start with 1, personally. Well, we also have the graph. We're not going to start with 1. Alright, so we're going to test, looks like 6. Let's test 6. What is it? 2, negative 11. 2, negative 44. When you choose down, that's going to be 12. On the head there. 2, 12, 1, 6, 8, 48, 4, 6 and 4 is going to become 4, 0. Cool. I now know 6 was an upper bound as well. Alright, so actually we probably could have started with 6, not fault. But we see this is an upper bound as well because they are all non-negative. Alright, so 6. That is a 0, and it's an upper bound. Alright. So, next, we see something in between 0 and negative 1 is also 0. Only thing out there is negative 1/2, so I didn't have to try it. Start with this. 2, 1, 8, 4. Negative 2 down, negative 1 times 2 is going to be negative 1, 0, 0, 8, negative what? 4, 0. 2, 0, 8, 0. Notice. Alright? We have both our zeros. Alright? So, we also know from looking at the graph there aren't any zeros. Alright? Now, had we not had a graph, obviously we would try 1, 2, 3, 4, anywhere I've got 6, but what do we do here? How do we know which ones we should check first? What might make it a little bit easier? Well, see, we have our upper bound, right? I'd probably start going backwards from my upper bound and from my lower bound. I would check the numbers closest to those first. Okay? Question about that? Why don't, well, let's do this. It's very dangerous to drive when you have sneeze because you cannot sneeze and not go dry. Right, if you sneeze, you have to put it back so you can sneeze. Or else your eyes are not like that. Alright. Determine an interval at which all real zeros of a given function must lie. Explain your reasoning using the upper and lower bound test. Then find all the real zeros. So let's look at this. Let's start off by going P. It's going to be the factors of negative 12, which is plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. These will be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Alright. What's the first thing we're going to want to do? Yeah, this is just finishing on this first a little bit. P is going to be all of those, so plus or minus 1, and then we have 1/2, 3 halves, and we have a third, 2/3, 4/3, and then 6, 2/3, 1/2. So, alright, so are you graphing yet? Alright, so you have 6x to the 4 plus 70x squared equal x squared plus 35x. Alright, so you graph this. Here's our graph. Over here. Alright, what appears to be upper bounds here? So, upper bound looks like it's going to be 1. What's the lower bound look like it's going to be? Right there, -2. We can try -2 first. Alright. So first off, you want to find the interval in which all the zeros fall. Alright, so we're going to try positive 1 first. Alright, and we're going to have 6, 70, -21, 35, -12, 76, 76. That's going to be what? 5, 5, 90, 90, 78. All right, all non-negative. Therefore, this is an upper bound. So 1 is an upper bound. So goodbye, positive 2, positive 3, positive 4, positive 6, positive 12, positive 4/3, and positive 3/2. You're all gone. You're useless to us. Oh, and goodbye, positive 1, because it's also not a 0. So now we only have 1, 2, 3, 4 positive numbers to try. All right, cool. Let's try. We said -2 would be our lower bound. So we have 6, 70, -21. Get ready with your calculator for the multiplication. 6 is down here. 12. But it's -12. So we're gonna have 70 plus -12 is what? All right, good. -2 times 58 is going to be some kind of negative number. -1. That's going to be negative. That's going to be a big column. 4. 7. Plus 254. 254. All right. That's going to be 299. And -2 times 299. It's going to be really negative.
Yeah.
That's going to be really negative.
598.
These are you're not alternate though. So now I'm concerned. 264. Concerned as to why this doesn't Hey guys, real quick, I want to go back here. Hey, I need you guys to focus. I need to make a clarifying point here. Alright, clarifying point. Alright. This says if C is less than or equal to 0. Alright. And every number in the last line of the division is alternately non-negative and non-positive. Then C is a lower bound. Alright. If C is greater than or equal to 0, and every number in the last line of the division is non-negative, then C is an upper bound for real zeros. Alright? So, let's go back here and look at this stuff. So, our options are this. Okay, first of all, we look at this, it says C is greater than 0, right? This positive 1. So if we go back and look, it says C is greater than 0 and every number in the last line of the division is not negative, and C is an upper bound for the real zeros above that, right? So this one doesn't really change anything, right? C is positive, all of these are non-negative, right? Therefore that's still an upper bound. Now in this case, C is negative, right? C has to be negative. So if C is negative, right? If C is less than or equal to 0, and every number in the last line of division is alternately non-negative and non-positive, then there is a lower bound. These are alternates. We have those, and then we have positive 2 as our leading coefficient, which gives us plus or minus 1, plus or minus 2. So what do we have to do after that? We're going to divide these ones, the factor of the constant by the factor of the leading coefficient, and that's going to give us P divided by Q. That's equal to 1. Okay, plus or minus 1, plus or minus 3, plus or minus 9, plus or minus 27, and then plus or minus 1/2, plus or minus 3/2, plus or minus 9/2, plus or minus 27/2. Alright. Also apply. I want to figure out. I'll read off the names. Something who's not on there. Brianna, Jericho, Leilani, Lucas, Michaela, Jill, Leilani, Michaela, and Jill are not on. So, the only people I'm missing. I still need for homework number 2, which was last night's homework. I need Jericho, Leilani, Lucas, Nicholas, Haley, and Sean. And then Leilani, Kayla, Dylan. And for homework number 1, I need Jericho, Leilani, Lucas, Mo, Nicholas, Sean, Jalen, and Kayla. Okay, those are the only 2 so far. Oh no, they did the extra. Alright, so at this point, we have numbers that we have to test, but what I would like to do is figure out if I have an upper or lower balance. So the first thing that I would do would be to, I'd graph this, alright? So, pull out my graphing calculator, there's a moment of my honeymoon right there. Alright, about 4 months, 5 months from now. Actually, pretty well. Alright, so we have y equals 2x to the 4th minus 13x squared to the third. I did that. Correct myself. Plus 21x squared plus 9x minus 27. Alright, we're going to graph it. Alright, so let's do Zoom 6 real quick just so we can zoom in on that. Yeah.
I want you to put my
you have old calculator that has updated? That's your normal calculator? Yeah. Oh, let's see. I might need to update the calculator again. So, well, let's see. Actually, no. Where is this thing? That is this in there. I don't know that in there. You see that is? Okay. So, at this point, you look at your graph, and if we look at this, we see, it looks like we can see our lower bound and our upper bound. Our lower bound is looking like it's by -1. Our upper bound is looking like it's by +3. So we want to check that. All right. So we're going to show that all of our zeros fall in between that range. Let's say -1, 2, -13, 21, 9, -27. Anyone remember, in order for this to be a lower bound, what's going to be true here? When we do our synthetic division, what's going to have to happen to these numbers up? Huh? Mixed values, every other one. Every other one's going to be what? So it's going to be, every other one's going to be non-negative, or non-negative, non-positive. So it's going to be non-positive, non-negative, non-positive, non-negative. So that's negative 1 times 3 is -2. 13, -13 plus -2 is -15. -1 plus 15, or -1 times -15 is going to be 15. It's going to be 36. -1 times 36 is -36. That's going to be -27. It's going to be +27. This is 0. So we figure out two things here. Number one, all right, -1 is actually a 0. All right. -1 is a 0. Number two, -1 is a lower bound because the numbers alternate. Because c is less than or equal to 0, the numbers alternate between non-negative, non-positive, non-negative, non-positive, non-negative. All right. Questions on that? So, at that point, we say, okay, well, we want to check, let's check this right here. All right. We said 3 looks like it's probably our upper bound. So we're going to check it again. And we're going to have 3. Now, we're going to use our original coefficients, or we're going to use these new coefficients. New ones, we have 2, -15, 36, -27. So if this is a up and down, what should be true? Oh, it's all going to be non-negative. So 3 times 2 is going to be 6. So it's saying that you want to find a number that's actually upper bound. So you have 2, 7 times 2 is 14, 1, 7 times 1 is 7, it would be 28. 28 times 7 is some big number, it's positive. That would be some big number, it's positive. Alright? And then 7 times some big number is positive, and bigger than 27, so it's going to be a positive number. So you get all positive numbers. So 7 would definitely be an upper bound. So what that would say is that all of our rational zeros, or all of our real zeros fall below 7, which Obviously they do. Alright? So, that is my bad misinterpreting the problem. But then what it does want you to do is to still figure out what are the zeros. Alright, so we have figured out that -1 is a zero. Alright. We also figured out that 3 is a zero. And if we're looking at our graph, we see that we have something between 1 and 2 as a zero. So that would give us an option of positive 3/2, because that's 1.5. So we'll try that one. We have 3/2. And 2, -9, and 9. And you 2 down. 3/2 times 2 is 3. That's going to be -6. 3/2 times -6 is going to be, let's see, it's going to be -9, 0. So that tells us that 3/2 is also a 0. Alright. And we know this should have how many zeros? 4. How do we know that? Because the exponent is, highest exponent is 4, therefore it has to have 4 real zeros. Not invisible, and we'll talk about that. You can only, invisibles, imaginary zeros, they come in pairs. You can't have one imaginary zero, you can't have 3 imaginary zeros, you can only have 2, 4, 6, 8. So what we have here, remember, each one of these, each time we do this, we can say, since we started with a exponent of 4, this would be 2x cubed minus 15x squared plus 36x minus 27. Alright, but then we found another zero. So this would be 2x squared minus 9x plus 9. And then we found another zero, so it would be 2x minus 6 equals, alright, so you have this factor. Well, 2x minus 6, we set that equal to 0. Add 6 on both sides. 2x equals 6. X equals 3. Alright. So what we have here is our zeros are -1, 3 happens twice, 3/2 happens once. Alright, so what we say about x equals 3 is it is yeah. So x equals 3 is a 0 with multiplicity Alright. X equals -1 and x equals 3/2 has a multiplicity of 1.
First you have them flat, so all you do is take the original equation.
Drop the exponent down by 1. I'll be honest with you. After this, you'll never use that. You'll never use this. You'll never use this idea. The idea of syntax division and factoring, you need to know. The idea of the upper bound and lower bound test, I've never used it. You'll never use it in calculus. Not that I can, and if you do, I can teach you calculus without even know. I don't teach it with it. Well, that's this is more of the analytical type of math. So here's what we have. All right. We have the rational zero theorem. All right. Someone tell me. What does the rational zero theorem allow us to do? What does it tell us? What does the rational zero theorem do?
Well,
Alright, so what does that mean? Did you guys hear what Mo said? That, it's not basically, that's what it is. What does the rational zero theorem allow us to find? Okay, which are our what? Those are called something. They are our possible what? I'll give you a hint. They are our possible, it's in the name of the theorem. Rational zeros. The rational zero theorem allows us to figure out where the function potentially crosses the x-axis. The rational zero theorem allows us to figure out where the function potentially crosses the x-axis. Upper and lower bound tests tell us where are these x-intercepts going to occur between. It allows us to figure out, are there any x-intercepts above a given point? Are there any x-intercepts below a given point? Alright? Now, we still need another one. So those both help us. So that you have the rational zero theorem. It could give you a bunch of possible rational zeros. Alright? The upper and lower bound test can help you eliminate some. Okay? But we do need some other potential ways to eliminate some of our options. And what that does, or what that is, the next way we have is called the Descartes rule of signs. Okay? So, the Descartes rule of signs will help us determine the number of positive real zeros and the number of negative real zeros. So I'll write that down. Okay. Mathematically, that's a sort of description of what the Descartes rule of signs helps us do. Mathematically, what the Descartes rule of signs says is if you have a polynomial with real coefficients, okay, then the number of positive real zeros of f is equal to the number of variations in sign of f of x or of x in that number by some even number. And the number of negative real zeros of f is the same as the number of variations in sign of f of negative x, or less than that by some even number. So I want you to write down the circle of signs will help us determine blah, 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 blah. And I want you to write down this so that you have the mathematical definition. Okay. This right here. Now, this part right here, you don't have to write all that. You just say, if a polynomial function with real coefficients. So you don't need to write f of x equals a sub n x to the n power plus a sub n minus 1 times x to the n minus 1. Don't write all that. Just know what it means. If f of x is a polynomial function with real coefficients, then all this is true. You guys write that? So this is used after you use the rational zeros. Now, what we're going to do is, quick side note, what it means by variation in sign is that the coefficients alternate in sign. Okay? So, for instance, if you're looking at this next one, well, it's easier to show you with an example. Alright? So describe the possible real zeros of g of x. equals negative 3x cubed plus 2x squared minus x minus 1. Alright? So there's two steps to this. Alright? Step number 1 is to look at the number of sign changes of f of x, in f of x. So we're going to look at, in this case, it's g of x, so g of x and f of x all the same. Alright, so I'm going to rewrite this. G of x is equal to negative 3x cubed plus 2x squared minus x minus 1. Alright? We're going to count the number of times the coefficients change sign. So this first coefficient is negative. The second coefficient is positive. That is one sign change. Okay. This coefficient 2 is positive 2. This coefficient is negative 1. That's a second sign change. From negative 1x to negative 1, that's not a sign change. So I'm going to give a little dash to represent no sign change. Alright? Sometimes that, so, does that make sense? Yeah. So there are two sign changes. Alright? Now, we'll go back here and look at this first. It says the number of positive real zeros of f is equal to the number of variations in sign of f of x. That's, I'm going to stop there. There's another part to it. Alright? So, what this is telling me is that there are there could be two positive real zeros. Alright? It could cross the x-axis 2 times on the positive side. So potentially this function could cross the x-axis twice over there. Alright? Here's one thing this tells us. That tells us that there cannot be 3 positives. This graph does not cross the x-axis on the positive side more than twice. It's going to be twice, or come back here. It says the number of positive real zeros of f is equal to the number of variations in sign of f of x, which is 2, or less than that number, so or less than 2, by some even number. So that means it can be less than that by an even number. And if you want to count, so an even number is 2. So this function could have 2 positive real zeros, or a even number less than that would be 2 minus 2, which would be 0. Positive real zeros. Okay? So this is a possibility. So what does this tell us? Well, number one, it tells us that there is either 2 positive zeros or 0 positive zeros. There's no in between. There's not going to be 1 0 that's positive. All right. If I find 1 0 that's positive, that tells me there has to be another one. Only one other one. It can't be. So there's not 3. There's not 1. There's either 2. This function either crosses the x-axis on the positive side twice or none. That makes sense. Yeah. Okay. So that's the positive real zeros. Positive y because it's g of positive x. So now we want to figure out, all right, because we know what? We know this thing has 3 zeros, right? So 2 of them could be positive. If 2 of them are positive, that would make the other one what? Negative. If 0 of them are positive, that makes the other ones what? Negative. That means, so if there are 2 positive real zeros, that means that there's 1 negative real zero. If there is 0 positive real zeros, that means that there has to be 3 negatives because there's 3 total. So let's check. We have g of negative x. Okay, so here's a little shortcut. The way g of negative x changes compared to g of x is if you look at the exponent, and the exponent is odd, the degree changes. Odd exponent, this changes into a positive PX2. Alright. Even exponent, this even exponent, this stays the same. Alright? This is an odd exponent. So that means that's going to change. It's going to change signs. Look, you pay attention? Alright? This doesn't have an exponent, so that's going to stay the same as well. Alright? Now,
Sign change.
we're going to do sign changes again. So is there a sign change there? No, because it goes positive 3, positive 2. No sign change. Positive 2, positive 1. No sign change. Alright? Positive 1 to negative 1. That's one sign change. Alright, so what does that tell us? Well, that tells us that the number of negative real zeros of f is the same as the number of sign changes of f of negative x. Okay? Well, there's one sign change, so that tells us that there is one not positive, one negative real zero. That's all. Let's think about what this is telling us now. Because if we go back and look at that, it tells us that the number of negative real zeros of f is the same as the number of sign changes of f of negative x, or less than that number by some even number. How do I find a number that's less than a number by an even number? I subtract 2. 1 minus 2 would be negative 1. I can't have negative 1 of something. Right? So I can't subtract 2 from here. Because I can't have negative 1 negative zeros. That's impossible. So that tells us that our only option is we know for a fact that this graph crosses the x-axis on the negative side one time. It has to. All right, now, which one, for this graph right here, it either has 2 positive or 0 positive real zeros. Which one does it have to be? Well, we know there's one negative. It has to be 2 positive. Why? There's 3 zeros altogether. So if we know for a fact that there is guaranteed to be one, there is one negative real zero. That means there's 2 other zeros that they have to be positive. If it was 0, we have 2 zeros that are missing. All right. Now, I do want to be careful here because I just realized I said something that could be a little, that's actually not 100% true. Alright? What I said is that there has to be 2 positive zeros. Alright? There is the potential that you get 2 imaginary zeros. Alright? So, it says, so here's the deal. You can have positive real zeros, you can have negative real zeros, and you can have imaginary zeros. Alright? So, we want to describe the possible real zeros. Okay, we have 2 positive or 0 positive, 1 negative. Alright? So what we like to do, I'm going to see if I can start calling this somewhere else. So what I like to do here is this. Alright, I'm going to jump ahead. I may talk about this later. So there's these things called imaginary zeros. Alright? So what you can have here is you can have positive zeros, negative zeros, or imaginary zeros. Alright? I'm going to make a table that describes the nature of my zeros. Alright? I know I could have 2 positive real zeros. Right? I know for a fact I have 1 negative real zero. 2 plus 1 is 3. 3 zeros. We said this function has 3 zeros. So how many imaginary zeros do we have? 0. Because when I add these numbers up, it has to equal 3. And there are only 3 zeros. I did it. So, now, this function, does it definitely have 2 positive real zeros? No, it could have 0. But it definitely has 1 negative. Alright, so that leaves over 2 zeros that haven't been used yet. So then they would be imaginary. Now, let's just look at the graph of this real quick. Let's just see what it has and see if all this matches up. Negative 3x squared, or to the third, plus 2x squared minus x minus 1. This graph better cross that x-axis one time on the negative side. There's the graph of that function. I want you to notice, okay, it definitely, we said it has to cross the x-axis on the negative side one time. Does it cross it at all on the positive side? No. That's cool because you said it could, that could be the case. So what that means is that this function has 1 negative real zero, no positive, but 2 imaginary real zeros, or 2 imaginary zeros. All right.
Because it says there has to be 3. It says the possibility of 2 being positive. If guarantees a negative, it means if there's 2 possibilities, it means the guarantee doesn't make 3. It could be go over 0.
And just you graph it, there's no positive real zero, so it has to be much.
No, it has to be 3 zeros, right? Why? That's right. Is the highest exponent before it. 3. So there has to be 3 zeros. So down here, we do this, we look at the sign changes. There's 2 sign changes. That means there's 2 positive real zeros or there's 0 positive real zeros. And this is the same thing with the g of negative x. It tells me that there's 1. There's 1 negative real zero. There's no argument about that. Definitely 1 negative real zero. So, I put these together. I could have 2 positives and 1 negative. That equals 3 zeros. 2 of them are positive, 1 of them are negative. There's no room for any imaginary zeros. I've already used all 3. Down here, alright, we said there's 0, and there's 1 negative, but none of them are positive, so the only things left are imaginary zeros, which leaves us with 2.
Like having 3 spots.
Yeah, 3 spots, when you add them up, and add up to 3, in this case. Alright? Look at this one. Alright, let's look at this one. So, Jericho, what's the first thing that we're going to do here? Trying to help them out. So we're going to find the sign changes of our original function. So is this going to help us find the positive zeros or the negative zeros? Okay, so it is going to help us find the positive zeros. Why is it going to help us find the positive zeros? It would say positive x.
Yeah.
So, between positive 6 and positive 8, is there a sign change? Between positive 8 and negative 10? Between negative 10 and negative 15? So that tells us that there are how many positive real zeros? 1. Is there any other numbers?
Yeah, four other negative, four other.
No, wait, what were you saying?
Maybe four other.
Yeah, I'm talking about, are there any, can there be any other possible positive zeros?
Yeah, one imaginary.
No.
No.
No, why can there not be any other positive zeros? Huh?
Actually, hold on, that can be because if we make the x there, h of x, make that negative.
That's talking about negative real zeros. I want to know, are there any other possible? Do we know for a fact that there's definitely one positive real zero, or is there other options like we had up there where you had a 2 or a 0? No. No, at least the rule says that the number of positive real zeros of f is equal to the number of sign changes of f of x, or less than that number by some even number.
Oh, there's not.
Well, I can subtract 2, but if I subtract 2, you get negative 1, and I can't have negative 1. Alright. So, there's definitely, for a fact, absolutely certain, one positive real zero. This function has to cross the x-axis somewhere on the positive side, for sure. Alright. Now we're going to look at the negative zeros, h of negative x. Alright. So, what do I do here? H of negative x. How do I figure out h of negative x? If the exponent is odd, what happens to the sign of the function? Or that term?
Oh, it changes on.
Change the sign. So is this exponent odd?
Yeah.
So it's negative 6x.
Yep.
Is this exponent odd? What?
No.
No, it stays the same. Is this exponent odd? Yes. What's 10x? Is this exponent odd? No, it doesn't have an exponent. Alright. So, negative 6 and positive 8. Is that a sign change? Positive 8 and positive 10. No, is that a sign change? No. Positive 10 and negative 15, is that a sign change? Yes. 2. Alright. So that tells me that there could be how many negative real zeros? Two negative real zeros. Alright, I know for a fact there are 2. Yes. 2? Why not?
No. Yeah, because you're still making zeros, you know.
It could, but I'm more concerned about whether or not I can have a different number of negative real zeros.
Zero.
Why? Subtract 2. It can be 0 negative real zeros. Alright, now we're going to make a table. So, I have options for the number of negative real zeros, no options for positive real zeros. So I'm going to go positive, negative, and for imaginary, I'm going to put odd. Odd is bad. Alright. So, start off. Positive zeros. How many of those are there?
One.
So,
Sure.
Sure, just one, alright? What about negative zeros? How many can we have?
2 or 0.
Okay, so you can have two, let's start there. So if we have one positive, two negative, that's 3. We know there's 5 total, how many does that leave for imaginary? 2. Alright? Now, we know for a fact is 1, positive. Now, what else, what is another option we can have for negative 0? 0. So if there's 1 and 0, so that's a total of 1 0, how many does that leave for imaginary? 4. 4, imaginary. Alright, so notice, again, I said imaginary is on pairs. 2, 4. You can't have 5, 3, or 1. So, yeah, let's graph this, just to see if, you're right.
This is really easy though. It's the easiest thing I can do.
6, you just said you gave me the right. Because he's gonna have to light us all cry. You think you get online, huh? YouTube. That doesn't make me happy. I mean, to watch math for an hour and a half on Saturday.
I got work Saturday also.
Oh, yeah, Sunday's gonna be a heck of a day.
I got work Sunday, what do you mean?
Alright, so, we said that there's definitely one positive real zero. Right there. We said that there could be 2 negative real zeros or 0 negative real zeros. Looks like there are 0 negative real zeros.
You put in
Alright, so what does that tell us? It tells us that there's definitely one positive, 0 negative, or imaginary. Alright? Questions about that? I do want to talk about one thing. So let's say this was that, let's say this came out, let's get a long one and ended up being like 7 sign changes. Happens. 7 sign changes. So you have 7, take away 2, you have 5, take away 2, you have 3, take away 2, you have 1.
you take any more than 3.
No, it's an even number. Yeah, well, if you take away 4, that's the same as like 8. That's the same as taking away 2 plus. Right? So, you guys write this down. Alright? Using the Descartes rule of signs, the number of real zeros indicated includes any repeated zeros. Alright? So a 0 with a multiplicity n should be considered as n zeros. So when something has a multiplicity of 2 or a multiplicity of 3, that means it counts as 2 zeros or 3 zeros. And then there's the definition of multiplicity, which we're kind of talking about. For fun, yeah. Just because it's in that number. I mean, you could always find ways to. You guys need to get better at summarizing stuff. So.
I was just asking questions. All that, so I'm just writing that shit down.
the Descartes rule of science, it counts, like, let's say positive 3 has a multiplicity of 2, that counts as 2 zeros. Okay? Now, when you have zeros, so if you're looking at the graph of a function, and you see the zeros, a zero that has a multiplicity of 2 or 4, an even multiplicity, it is going to look like a parabolic shape. It's going to look like a U. You can go a U that's upright or a U that's upside down. Okay? And if a zero has a multiplicity of 2, 4, 6, an even multiplicity, it does not pass through the x-axis. You can already go back. Graphs. Right here. This zero right here has a multiplicity of 2. Right? We found that. We saw that it had more because we have 3 and we have x equals 3. We know it has a multiplicity of 2 because it looks like a parabola right there. And it does not cross the x-axis. Alright? This zero and this zero on the other hand, they have a multiplicity of 1. Okay? Because they go straight through the x-axis. They cross through the x-axis. So first of all, they cross the x-axis, so we know for a fact that they have an odd multiplicity. We know it's 1 because they go straight through. If it was a multiplicity of 3 or higher, it would start to look something like this. We go here, that. If that was a 0, that 0 would have a multiplicity of like 3. It looks like it's a function. Make sense? So the multiplicity of this kind of describes what the shape of the graph looks like as the zeros. So this don't necessarily need to write that unless you want to. We've talked about this already. It is very important. I kind of jumped ahead. All what this is telling you is that if a polynomial is a 6-degree polynomial, it has 6 zeros. They could be real, they could be imaginary. It has 6. That's what it's telling you. All right. So you can have, so if you have a 6-degree polynomial, that means that you could have, you could have some positive zeros, you could have some negative zeros, and some imaginary zeros. You could just have negative and imaginary. You could have positive and imaginary. You could have just positive and negative. All right. But what we do know is that you add up all the number of zeros, you get 6. Because it's 6-degree polynomial. Probably shouldn't make you write it down because that's what that's what we call a fundamental theorem of algebra. All right, it's in your book, but all it's saying is 15-degree polynomial has 15 zeros. Yes, basically. 90. All right. So what we can do is get to the point where we can actually take what our zeros, if we know what our zeros are, and write a possible equation for it. So if I told you that the zeros are 3, -3, 2, and 4, you can write a potential linear factorization of that equation. All right. So the one thing that you do need to know is that complex, or what we call imaginary zeros, they come in pairs. If there's one, there has to be another. Right? You can't have 3. So in pairs. Okay. So what we get here is this. It says write a polynomial of least degree. So I want you to write this down. So what we want to do is we're told, I'm telling you guys that, okay, this polynomial, right, of least degree, has the real coefficients in standard form, or we want to write a polynomial of of least degree with real coefficients in standard form that has the zeros, -2 for 3i or 3 minus I has zeros. All right. Now, in order to do this, what we have to understand is that when we have our zeros, we can write them as linear factors. Okay. And what that means is, if we have, so our zeros are x equals -2, x equals +4, x equals 3 minus I, right? And so it's an imaginary zero, right? Since this is an imaginary zero, it means there has to be a second one. So what we do, and what we know, is, so if you have something where you have an imaginary zero, it's a plus bi, then its conjugate, a minus bi, is also a zero. So if a plus bi is a zero, a minus bi is a zero. If a minus bi is a zero, a plus bi is a zero. So if x equals 3 minus I is a zero, that would mean that x equals 3 plus I also has to be a zero. Alright. Did you guys last year deal with imaginary numbers at all? Did you guys do imaginary zeros or imaginary numbers? Alright, Monday we may be doing something with imaginary numbers. Alright, so let's look at this. So x equals -2. We can write that, this is our zero. We can write that as a linear factor by moving x, by getting something set equal to 0. So we're just going to add 2 to both sides. This right here is a linear factor. I should have asked if you guys knew about imaginary zeros beforehand. Okay. Alright. Right here. I want to get this set equal to 0, so I'm going to subtract 4 from both sides. You get x minus 4 equals 0. That is also a linear factor. Alright? You get that far? The imaginary zeros get a little bit more fun. So what we're going to do is, I'm going to subtract 3 and I both sides. So I get x minus 3 plus I equals 0. That is also a linear factor. I'm going to come over here. Subtract 3, subtract I on both sides. X minus 3 minus I is equal to 0. So I have my 4 linear factors. Okay? So, once I have my linear factors, this right here, over here, that I wrote on this board, this is also linear factor. These are also linear factors. So I'm going to write something like this. So my polynomial, I'm going to say f of x is equal to linear factor number 1 times linear factor number 2 times linear factor number 3 times, and here's factor number 4. Okay? I'll be honest, we don't want those imaginary numbers. If I can't graph that on my calculator. Alright? So what we have to do here, we have to expand this. So, x times x is x squared. X times negative 4 is negative 4x. Alright? 2 times x is positive 2x. 2 times negative 4 is negative 8. I expanded those two. I'm always going to expand the complex zeros together. So what I mean by that is I'm definitely going to go multiply this one by this one. So x times x is squared. X times negative 3 is negative 3x. X times negative I is minus ix. Just treat I as a variable. Minus ix. Okay. Then I'm going to have negative 3 times x is negative 3x. Negative 3 times negative 3, that's positive 9. Negative 3 times I, that is, or negative 3 times negative I, that's going to be positive 3i. Here's the thing. At the end of this, we should have no more i's. Okay? So then finally, you're going to do I times x. That's going to be positive ix. I times negative 3, that's going to be negative 3i. Alright? And then I times negative I. Okay, anyone know what that is? No, I times I is ultimate. This is I squared. You know what I squared is? Okay. This is what I is. So square root of negative 1. So it allows us to take the square root of negative numbers. Alright? So if the square root of I, or the square root of negative 1 is equal to I, then I squared is equal to negative 1. Okay? We're going to talk about imaginary zeros on Monday. Okay? So I squared is equal to negative 1. Now, what does that mean? Well, we have I times negative I, which is going to be minus I squared. We're going to put that for now. We're going to simplify all this. Right? So it looks like a lot. That's fine. Just remain calm. We have x squared. Negative 4x plus 2x is negative 2x. Minus 8. Okay? Now, whole bunch of stuff. Remain calm. X squared. Is there any other x squared in here? Negative 3x minus 3x. That's negative 6x. There's no other x's in there. Right? So top, yeah, like term. Negative 3x and negative 3x. So it's going to be minus 6x. Now you have minus ix and plus ix. Those go away. They cancel out, right? So minus ix plus ix. That goes away. 3i minus 3i. That goes away. Plus 1, or plus 9. Then, I know I squared is equal to negative 1. Right? So I have I squared. That's negative 1. And then I have minus negative 1, which turns into plus 1. That's equal to x squared minus 2x minus 8 times x squared minus 6x plus 10. Notice there's no more i's. No more i's. Alright? And then the last thing that you would want to do is take this and expand it. So do I need to draw these lines if I talk it through? Alright, so it's going to be x squared times x squared, that's going to be x to the fourth. X squared times negative 6x is negative 6x cubed. X squared times positive 10, that's plus 10x. Negative 2x times negative 6x, that's positive 12x squared. Oh, I skipped one, calm down. Negative 2x times x squared is negative 2x cubed. Negative 2x times negative 6x is positive 12x squared. Negative 2x times positive 10 is negative 20x. And then negative 8 times positive x squared is negative 8x squared. Negative 8 times negative 6x is going to be positive 48x. And then negative 8 times positive 10 is negative 8. I won't give you any of these problems. Homework together at 12. I'm not kidding.
Yeah,
I am kidding. You don't get 12. But I simplify this. X to the fourth. Negative 6x cubed, negative 2x cubed. That's going to be negative 8x cubed. We have negative or positive 12x squared, negative 8x squared. That's going to be positive 4x squared. 10x plus negative or minus 20x is negative 10x plus 48x is going to be positive 38x. And I'm going to have minus 8. And after all that, what that tells me is that you have this polynomial right here, this one, and only this, but not only, but this polynomial right here has the zeros negative 2, positive 4, 3 minus I, and 3 plus I. That's 4 zeros. Exponent is 4. Makes sense. Look at this. 1 sign change, 2 sign changes, 3 sign changes. So that means that this polynomial either has 3 positive real zeros or 1 positive real zero. I guess it has 1 positive real zero. Mind blown.
yeah.
We'll spend another day on this for your homework. All right. You are doing page 94, 10 and 12. Just 10. So you're doing 10 and 12, and you're doing 26, 28. That's 4. And 32 and 34. On 10 and 12, it says solve each equation. What that means is find the zeros. So you can use the rational zero theorem. You can use this sort rule of signs. You're going to use synthetic division. You want to find out which of those possible zeros are actually zeros. 10, 12, 26, 28, 32, 34. This is the first 6.
Can't get my color here.